Hello, and welcome to the very first episode of our Ultrasound Physics series. This course is based on understanding ultrasound physics by Dr. Sidney K. Edelman, and throughout these 24 chapters, you'll build your understanding of ultrasound completely from the ground up. Before we begin talking about sound waves, Doppler, image formation, or ultrasound artifacts, we first need to learn the language of ultrasound physics. Because ultrasound is a world full of numbers, graphs, equations, measurements, and relationships. But here's an important question. Can we really understand all this information if we don't understand its language? That's exactly what this first chapter is about. We'll start with the fundamentals. From reading a simple graph to understanding scientific notation, measurement units, and the metric system. The very first step towards understanding data is learning how to visualize it. The human brain is exceptionally good at recognizing visual patterns. Graphs take large collections of numbers and transform them into simple pictures that our brains can understand almost instantly. Every graph you will ever see is built on two simple axes. Think of them as a map. The horizontal axis, or the x-axis, tells us how far to move left or right. The vertical axis, or the y-axis, tells us how far to move up or down. Every point on a graph is simply an address on that map. Now that we can read graphs, it's time to understand the stories they tell us. These stories are called relationships. A relationship describes how one variable changes in response to another. Throughout ultrasound physics, we'll repeatedly encounter 5 basic types of relationships. The first is simply called related or proportional. For example, weight is related to dieting. Santa Claus is related to Christmas. Exam score is related to or proportional to studying. And dental health is related to flossing. The simplest and probably the most common relationship is the direct relationship. When one variable increases, the other increases as well. The graph reflects exactly that. Notice how the line rises steadily from left to right. Both variables increase together. Here are a few familiar examples. Clothing size is directly proportional to one's weight. Age is directly related to experience. And skill is directly proportional to practice. But not every relationship works that way. Sometimes it's more like a seesaw. As one side goes up, the other comes down. That's called an inverse relationship. Its graph is essentially the mirror image of a direct relationship. For example, golf score is inversely related to skill, and grades in school are inversely proportional to partying time. There's also a special type of inverse relationship called a reciprocal relationship. In this case, multiplying the two values together always equals 1. For example, 2 and 1/2, 10 and 1/10, and one of the most important reciprocal relationships in ultrasound physics, period and frequency. Sometimes, however, two variables have absolutely nothing to do with each other. We call this unrelated, two things that are not associated. For example, hair color is unrelated to shoe size. Weight is unrelated to day of birth, and temperature is unrelated to day of the week. Relationships are built using numbers, but numbers are meaningless without units. Think of units as a number's last name. They give numbers their identity. Listen to this sentence. Sarah is 6. Something's off. It feels incomplete, doesn't it? 6 what? 6 years old? 6 months old? 6 days old? Without the unit, the number tells us almost nothing. That's why units are so important. They provide a common language for describing the physical world. One of the most common quantities we measure in ultrasound is length. Length is typically measured in millimeters or centimeters. For example, in the image on the left, the vessel diameter measures 21 millimeters, or 2.1 centimeters. In the image on the right, the perimeter of 2 cysts has been measured using the trace tool. One measures 0.72 centimeters, and the other 0.67 centimeters. Another important quantity is area, which is usually expressed in square centimeters. In the image on the left, the trace tool measures a cyst with an area of 9 square millimeters. On the right, two measurements have been made in a stenotic blood vessel. The first represents the total vessel area, which is 0.373 square centimeters. The second represents the remaining open lumen, 0.270 square centimeters. Comparing these two values allows us to estimate the percentage of stenosis. Another commonly measured quantity is volume, usually expressed in cubic centimeters or milliliters. A common example is measuring the bladder volume. To do this, we need two ultrasound views. The longitudinal view provides the bladder height, the transverse view provides its width and length. Using these three dimensions, the ultrasound system automatically calculates the bladder volume. In this example, the bladder volume is 180.4 cubic centimeters. But what if the ultrasound machine doesn't include an automatic bladder volume calculation? Fortunately, we can calculate it ourselves. The bladder isn't a cube. It's much closer to an ellipsoid. So simply multiplying the three dimensions together would overestimate its volume. Modern ultrasound systems use the following equation: length times width times height times 0.52. This constant, 0.52, is simply an approximation of pi divided by 6, which comes directly from the mathematical formula for the volume of an ellipsoid. Older references sometimes used 0.7, but this empirical approximation is no longer considered the standard in modern ultrasound systems. As long as units are used consistently, any properly defined unit is acceptable. Although it may sound strange, you could even measure your age in seconds. The calculation would still be correct. You'll also hear expressions like increase by a factor of 6. That simply means multiplying by 6. Likewise, decrease by a factor of 3 means dividing by 3. And remember, percentages are dimensionless. They have no units. Any physical quantity can be expressed using different units. For example, length may be measured in millimeters, centimeters, or meters. Converting between these units doesn't change the physical quantity itself. It only changes how we express it. 1 meter equals 100 centimeters, or 1000 millimeters. The measurement stays exactly the same, only the scale changes. Sometimes we work with numbers that are incredibly large or incredibly small. Writing all those zeros is inconvenient and increases the chance of mistakes. That's where scientific notation becomes extremely useful. Numbers greater than 10 use positive powers of 10. Numbers smaller than 1 use negative powers, and numbers between 1 and 10 simply have an exponent of 0. Now, how do we represent these numbers using scientific notation? The process is easy. Move the decimal point until only one non-zero digit remains to its left, and the resulting number is between 1 and 10. Then count how many places you moved it. That number becomes the exponent. For 1 million, we move the decimal point 6 places to the left. The result is 1 times 10 to the power of 6. For the next very small number, we move the decimal point 7 places to the right. The result becomes 1.24 times 10 to the power of minus 7. In the third example, again, we move back the decimal point 3 places to reach 1.742 times 10 to the power of 3. And the last number, which is already between 1 and 10, stays the same. Scientific notation makes large and small numbers much easier to read, write, and compare. This same idea leads directly to the metric system. Nearly all of science uses the metric system because it's logical, consistent, and entirely based on powers of 10. Prefixes are simply convenient names for these powers. Kilo means 1000, mega means 1 million, giga means 1 billion, and milli means 1,000th. For example, when someone says a flash drive has 16 gigabytes of storage, they're referring to approximately 16 billion bytes. One elegant feature of the metric system is that every large prefix has a corresponding small prefix. For example, giga represents 1 billion, nano represents 1 billionth. This symmetry makes the metric system remarkably intuitive and easy to use. Before we finish, here's one more pair of prefixes you'll encounter all the time: macro and micro. In many situations they aren't used as exact metric prefixes, but simply as descriptive terms. Macro means relatively large, and micro means relatively small. For example, a macroscopic structure can be seen with the naked eye, while a microscopic structure can only be seen with a microscope. This concludes the first chapter of our ultrasound physics series. In the next episode, we'll begin exploring the true foundation of ultrasound imaging: sound.